actually begun to find them. And I think what has happened is that until recently, most sea ice cruises have kind of been in this kind of region, and we've only seen ice down to about -6. We've now become a little bit more adventurous with what we're doing, and we're actually measuring, taking samples down in -10 and below. And what we found is that this is from one of these brines, absolutely littered with solid calcium carbonate crystals. Now you say, well, why on earth is this important? It's not biology. Well, it is very important, because if you look at how calcium carbonate forms from calcium ions and bicarbonate ions and forms, you form the calcium carbonate, you release some CO2 as well as the water. And then when you the dissolution is the other way. Well, if we're getting a humongous amount of calcium carbonate precipitating out in sea ice due to pure physical chemical reasons, that would mean that there's an awful lot of CO2 being released into these cold brines. So that these cold brines are very CO2 rich, and that means that the whole concept of the boundary layer of CO2 dynamics in polar regions in winter may have to be dramatically rethought. Well, okay, that's what we say when we're writing grant proposals, but actually, it's actually true. If we're measuring grams of calcium carbonate in the sea ice cores. It's not just a small amount. So that's quite an exciting thing that is taking up our attention. And these calcium carbonate crystals sometimes it's quite intriguing. Look at this one. It's actually formed a cast of the brine channel from which it came out of. So my guess is that the whole of the brine channel was no longer filled with brine, but in this case was filled with a solid calcium carbonate. So some of the other crystals are more routinely formed, and actually it's a form of calcium carbonate. It's ichite, and ichite is a rare form of calcium carbonate that doesn't. It's found in quite a few deep sea sediments, and now is found in sea ice as well. But so what is the dynamics of the brine channel system when you actually put a solid phase of calcium carbonate in there? Well, that's intriguing to know, and maybe is intriguing for when we're thinking about systems elsewhere.
What are the sizes there?
Was there?
Oh, that's a millimeter. Okay, it's a millimeter like.
No, this is an eyepiece graticle. So this is. So that's half a millimeter. Yeah.
And how did you do this?
So this particular sample that you see here, this was literally, we took the ice, sawed it into 10 centimeter sections and just melted it and just collected the debris that came off the bottom of the pot. Mm-hmm. So this is, but actually the warming of the ice would actually dissolve some of it rather than actually, so it's not coming from the melting process. In fact, this is, by default, it's an underestimate of what is there in reality. So yeah, just 10 centimeter sections. But I mean, we can now that it's been published and people well, actually you see the scale here directly. That's a millimeter scale. We're now getting reports of people from Barrow saying we go to Barrow at certain times of the year and the whole thing's covered in sand. Well, my guess is that it may likely be that it's actually calcium carbonate crystals that they're saying. It's just I don't think for some reason nobody's really looked before, even though we knew it should actually happen. And there's also quite a lot of calcium carbonate crystals found in the Italians have claimed that near de Mondeville that they've got in their in their glacial ice that they've got a lot of calcium carbonate crystals in that as well. So I don't know where that comes from. So, but what may happen is, so that's on a coastal site, and so my guess is that could be windblown from the system. Anyway, so that's an aside, but it's an exciting aside, I think. Back to so we certainly saw pictures like this before. You know, your average ice flow has a temperature gradient from the top to the bottom. This is always going to be at the melting or the freezing point of seawater, depending on which way you look at it. That invokes a corresponding change in the salinity of the brine. I'm talking about the brine salinity here, and of course the brine volume as well. So at the top in cold ice, there's a smaller brine volume, and down at the bottom of the ice where the brine volume is more. In the last talk, I got hooked up a lot on light. Well, in a lump of ice 1.5 meters thick, The incident radiation, say 1 to 5%, gets to the bottom of it if there is no snow. You put some snow on top of it, even a very thin sprinkling of snow of a few centimeters, and very little light is able to penetrate to the bottom of the ice floe. Now, I did say that many of these diatoms and many of these species are very low light adapted. They're absolutely crammed full of light harvesting pigments, but still, you know, this is at the borderline of kind of where they're able to grow. So within this labyrinth, so we've moved on from, you know, if you're thinking of the ice as being this Swiss cheese or sponge filled with a very cold brine solution, and this is the picture that was shown earlier, and you can see that within some of these channels and pores you get these brown blobs. Now these brown blobs are the diatoms that I introduced in the last lecture. Already this is a picture, a light microscope picture that was taken by Christopher Krebs. Already it's fascinating. This is a brine channel system that ends in a dead end. So the only chance for exchange of anything, gases, nutrients or whatever, is through here. But you will see already there's kind of a very isolated pocket up here that contains some diatoms as well. So this whole concept of connectivity, porosity, whatever way you want to think about it, is absolutely crucial when we're thinking about organisms needing replenishment of nutrients and also getting rid of toxic substances, but also a copepod, a small copepod albeit, could swim in here and could graze all of these things quite happily. Certainly a protozoan or anything else could kind of come in here and just eat this assemblage. I won't call it a community, this assemblage. Whereas this one is pretty protected from grazing organisms as well. So this is where this whole business of complexity of the system becomes interesting. In here, you could imagine that the bacteria, you know, a bacteria cell here that finds itself up here, it's got a long distance to go before it comes into any contact with organic matter that is excreted or produced by dead or dying cells down here. Whereas then a bacteria cell that finds itself within that kind of pocket, it's a very close proximity to the organisms that are producing organic matter. So it kind of just exemplifies those kind of like issues that we talked about before.
So is there a good constraint on what kind of fluxes you need to channel that small to feed that kind of population?
Those calculations could be made, as far as I know. Nobody's ever done that kind of thing, but I mean, you could certainly do that. I mean, you could actually, in this particular picture, you could actually work out what the biomass is pretty realistically, because you know the cells, size of the cells, you know what they contain as far as carbon, nitrogen, phosphorus. So you could actually work out the demands. It wouldn't be that difficult a thing to do, actually. So, I said that the major diatoms are the bacteria and the diatoms and the bacteria. Again, I will repeat what I said before. They are the best studied. The diatoms because they're so easy to see and because they're so easily preserved because of the strength of their silicate frustules, and the bacteria because they're relatively easy to stain. And the people that started looking at sea ice with gusto in the early part of Neil Sullivan and his group, you know, they were microbiologists that were used to staining things to look at bacteria and count bacteria, and that's why they're the most studied. We are now beginning to see that there's other things in there. But if you look at some data from this is Antarctic sea ice now, and just look at chlorophyll concentration in micrograms per liter as an estimate of biomass of the diatoms, and just plot that against ice salinity. This is not the brine salinity, this is the bulk salinity. So this is, if you take a 10 centimeter section of ice and you just melt the whole thing, so as well as the brine within that section of ice, you've also got all the ice matrix as well, so that's why the salinities are low. And you just plot that up. Normally, in this part of the world, chlorophyll values of about 4 are the absolute maximum. So 4 is really, in open waters, is the most you're ever going to get. And here you're getting values, well, take this 700 out, you're getting values up to 700, but certainly you're getting values in the high hundreds, and a lot of values above, or most of the values are above 50. So you're getting, it's just indicating there's a lot of biomass there. But again, if you look at the numbers of bacteria, in marine systems, this is number of bacteria numbers per litre of liquid. Normally you get to the power of 6. And something to the power of 6 as a general rule of thumb. There you're getting orders of magnitude more bacteria within the ice than you would find in open water. It's not particularly correlated with the algal biomass. There's no particular correlation with anything else, but you're just getting a lot of that. So there's so much biology that the ice has actually turned this coffee brown coloration, and that is kind of a common feature that you see in many parts of the world. But remember again what I said before, that we're not dealing with just these small components. We're dealing with a whole microbial network of lots of different classes and groups of organisms that are all kind of interacting in one way or another. These arrows look as though they're around them, but they're not really around them. But everything is producing the dissolved organic matter into the system, which is fueling the heterotrophic, which is fueling the bacterial dynamics within the system. And of course you have these things that I introduced at the very beginning of the talk, these larger organisms like the krill, these big crustaceans, they can't actually get up into the ice, but they can sit at the edges of the ice grazing on the organisms that are there. So they're also playing a role within this system. Obviously something taking a long time to load in this next picture. So what we find is when you look at the zooplankton, so crustaceans mainly here, you have the certain species that actually have their life history that is actually geared very closely with the seasonal cycle in the ice. So they have certain stages that are only found in surface waters in the summer. They kind of lay their eggs in the autumn, and their smaller life history stages are found in the ice. They develop within the ice, and then they're released into the ice from the ice in the early spring. So we have to consider these zooplankton as being, they're grazing, so they're using the resource of the ice, they're actually using the food that's within the ice, but they're also producing, and they're producing fecal pellets, so they're producing fecal matter, which varies in sizes from a few microns to quite large fecal pellets. Now these are contained within membranes, and why they're important is because if you look at these fecal pellets, you can see that a lot of the cells inside of them are really quite intact. Now this sinking through the water column sinks at a very much faster rate than a single cell sinking on its own. So by packaging this material in this fecal pellet biomass, it actually increases the chance of carbon that is being produced at the top of the ocean in the ice actually being packaged into a very fast falling projectile that actually gets sequestered into the sea floor. And sometimes you can go to, or there are reports definitely in the early literature, of ice floes being almost coloured black. And it's not coloured black by sediment, it's actually being coloured black by fecal material of crustaceans as well. I think it was a little bit fanciful. I can't believe it was actually black, but there you go. So they're important. There's a whole range of them. Some of them look like this. This is a Harpacticoid copepod taken directly from the ice. This is a big egg sac that is contained by the species, so it's actually reproducing and producing its eggs within the ice. This particular species or group of organisms is quite often found in sediments in other marine systems, so in the estuary and Menai Bridge you can find lots of Harpacticoid copepods living between sand granules within the sediments. Well, it's a similar kind of interstitial existence as these organisms must have within the ice as well. So large numbers of Harpacticoid copepods found in the ice, feeding directly on the ice algae and also the bacteria that are there. Well, you can just, basically you may be able to see some sausage-shaped organisms here. These are flatworms, turbularians, up to a millimetre long. They live, they're a very dominant feature of the grazers that are within the Antarctic ice. If you look at the grazers here, these are the Harpacticoid copepods, these are another type of copepods, and these are the turbularians. An awful lot of turbularian biomass within the ice. Now what they do is that they're osmoconformers, which means that as the salinity of the medium around them goes up, they actually shrink in size. So if you think about this, as the salinity of the brine in the brine channels goes up, they're shrinking. So the brine space is getting narrower and narrower and narrower. The salinity is going up, and they're shrinking. So that means that they're able to go through very much more of the ice channel labyrinth than many of their other counterparts. This harpacticoid I showed you before, it's got a hard exoskeleton. It can't shrink, it can't do anything. It basically, if the brine channel narrows around it, it's going to get squashed and it's going to pop. Whereas these things can change their shape and can actually twist and turn through the brine channel system, and therefore that's one of the reasons, or probably the main reason, why they're the predominant grazer in Antarctic ice. In Arctic ice, you certainly do find turbularians, but what you also find is ciliates, which I'll come into, I think, in the next slide, but also nematode worms as well. And nematode worms, as you know, are very long, narrow, pointed, ideal kind of for twisting and turning through brine channel systems. They don't change their shape in response to the salinity, but they're ideal for getting into parts of the ice that other things can't. And so turbularians, and the intriguing thing is, there's an awful lot of nematodes in the Antarctic open waters. They're teeming with nematodes in Antarctic systems, but we've never ever found, one person has found one nematode in Antarctic ice. Arctic ice is full of it. You find nematodes in every lump of ice you look at. You never find them, except this one occasion, in the Antarctic, and we have no concept as to why that could possibly be. You have these things, these are the rotifers, so these are ciliated protozoans. You can see that they're covered in ciliates. They also shrink with increasing salinity. They're able to kind of waft and twist and turn and change their body shape to get into the ice, and they're found in abundance, especially in the Arctic. Then you also have these calcareous organisms, foraminiferan. They're protozoans. They eat algae. They lay down these calcium carbonate encasings around the cells, and again you find huge numbers of those in Antarctic ice, but you don't find many in the Arctic ice. And again, they're there in the Arctic, they're in large numbers, but we're not quite sure. It could be just that people haven't been looking, so the Arctic researchers haven't looked for forams, whereas the Antarctic researchers have. So there's a variety of organisms that are in there that are eating these other things. Now, again, remember, photosynthesis produces oxygen, consumes carbon dioxide, respiration is the opposite. When we look at inorganic carbon in the oceans, it's a little bit more complex than this. If you take the normal pH of seawater, let's say it's between 7 or 8, the majority of that carbon is in the form of the bicarbonate ions, and there's actually very little free CO2 within the system. Okay, so the majority of the carbon dioxide or the carbon within the system is there as bicarbonate ions, and the tiny bit is carbonates, and most of it's in H form. Now, if we take, this is exactly the same set of samples as the chlorophyll and the bacteria that I've shown you. DIC, dissolved inorganic carbon, is basically the carbonate ions with this little bit of CO2 added to it. So what I've done is I've plotted inorganic carbon within the brines and plotted that against oxygen. Now remember, I said there's a lot of photosynthesis going on. It produces a lot of oxygen. It also consumes carbon dioxide. This is typical seawater values. This is what you kind of measure. This is the kind of range you get when you measure these parameters in seawater. So what you can see is that there's an awful lot of oxygen in the brines. And also, there is a general trend, not brilliant trend, but there is a certain number of samples with very decreased carbon, or dissolved inorganic carbon signatures as well. It's pointing towards a very strongly photosynthetic situation where a lot of oxygen going on and carbon dioxide being replaced. And if you actually take a look at these samples in a little bit more detail and just plot the CO2 against the dissolved inorganic carbon, so you just plot this little component against that, you can see that actually the CO2 depletion is almost, well, on a couple of occasions goes down to 0, so they are taking up all of the CO2 which is within that system. one of the consequences for that is that you get a very high pH. So we have measured pHs of the brine channel system. Normal pHs in seawater are about 8. We've measured pHs up to about 13 within the brine channel system, and that's brought about by these gas exchange problems. So you also, I said that you get a lot of ammonium, or you can get a lot of ammonium. Sorry, there should be a 4 here. It's the ammonium ion. Ammonia itself is obviously toxic, so we are dealing with the ammonium ion here. This is, again, plotted against the biomass within the ice. And this is what you would expect. This is normal seawater ranges of ammonium, really very low levels. And you can see that you're getting up to 200 micromolar ammonium. These are staggering numbers for marine systems. So the ammonium there is in high amounts. You've got high dissolved organic matter systems as well. So as well as ammonium being there, you're getting, this is normal seawater values. You can just see that there's a lot more organic matter within these brine channel systems than you would normally ever expect in this part of the world, in the seawater. So high ammonium, high dissolved organic matter, low CO2, high oxygen. So a lot of photosynthesis, a lot of organic matter being produced as well. If you look at the nitrate, now remember I said that nitrate is the predominant nitrogen species that is taken up by organisms within marine systems. You can see even at the high chlorophyll, so at the very high biomass, yes, you do get some values where nitrate has been exhausted, so it's clearly supported that high biomass. But you get some remarkably high biomasses where nitrate is there in high amounts as well. And this kind of indicates that there has been either the biomass has been ammonium based, so they've switched from using ammonia for nitrogen rather than nitrate, or that there's been a lot of bacterial activity within those brine channels that has remineralized or replaced the nitrate that is being used up. So you've got high amounts of organic matter, therefore that's supporting these very high bacteria numbers that are therefore they to break down the organic matter to release the nitrate back into the system. So if you add all of the nitrogen species up, so you add your ammonium and the nitrate and everything else that could be used, even in these colossal biomasses, and this is really a very rich system. Remember I said that in open, values of 4 are outstanding in the open waters. There's actually plenty of nitrogen to support more growth of photosynthetic organisms. Nitrogen is not limiting even despite the fact that the biomasses are really high. So this is why the sea ice has often been called, if you like, chemostats within the ice. So you've brought the bacteria into very close contact with the organic matter so that the whole coupling of this microbial loop is just very much more condensed and takes place very much faster than you would get in the open ocean. The only other places where it kind of equates to this is probably biofilms or sediment interactions in the ocean floor or in estuaries and places like that.
So if you took a volume of seawater and you froze it without any of the organic processes going on, but with all the organic molecules, what kind of concentrations would you end up with? I.e., if you enriched the values simply by taking that water, freezing it into ice, and having presumably some of these things would be rejected by the ice matrix. What kind of?
Yeah, well, what basically it falls on a dilution line. So basically, so it should follow. You know that gradient I showed you of temperature versus salinity. Basically, just like sodium and chloride or whatever, they should all fall on a similar kind of gradient. Yeah. So everything above that gradient is biologically produced, and everything below that gradient is biologically consumed. So and all of these things are falling way off.
So those are still way above.
Yeah, they're orders of magnitude above what you get. So yeah.
Okay.
Yeah, I was just trying to think. I don't have easily accessible. Quite often, what we do is just plot the whatever values against salinity and see where they fall onto that. It's not just the nitrogen that is being regenerated in these colossal amounts. You'll also find the same argument with phosphorus. So remember, phosphorus is also needed for the biology. It's just there in humongous amounts. And again, bacteria, or marine bacteria, are noted to regenerate phosphorus or phosphate really very quickly. And this is just a reflection of these high bacterial numbers regenerating a lot of this organic matter. So now remember, silicate. Now you would expect these diatoms, and this was largely diatom-based growth, they need a lot of silica to build these silicate frustules. I mean, they can't do it without it. Now, there's no way in the normal system you could get to these biomasses without silica being totally depleted. So there must be a regeneration of silica within the ice through microbial processes. And one of the ways you measure silica, or biogenic silica, is the first step is you put it in to a strongly alkali solution. So, and I said that all these gas changes that I explained, so the low CO2 environment has risen the pH up to about 12, or anywhere between 10 and 13. So what we think is happening is that these diatoms are being very much more quickly dissolved away by the high pHs of the brines than ever they would see in nature. Normally these diatom frustules dissolve away extremely slowly, but my guess is that these high pHs that we get within the brines, they're dissolving very quickly, which is why silica is not depleted. So what do we know about sea ice biogeochemistry? Well, this is, we know that there's a restricted exchange. We know that you can measure, and we frequently do measure, very high oxygen concentrations, low CO2 concentrations, high pH. As I say, when I made this slide, it was up to 11, it's now up to 13. High ammonium, high dissolved organic matter production, and high heterotrophic regeneration of nitrogen, silicate, phosphorus, and whatever else you care to mention. So that's the general picture that you see when people talk about where we're at with biogeochemistry of sea ice. We do have a little bit of a conundrum here, because the oxygen and the CO2 data point to a dominating photosynthetic signal, autotrophs. The photosynthesis is what's dominating. But this whole thing about the nutrients and the dissolved organic matter and this regeneration of all of these nutrients and remineralization tend to indicate that it's the bacteria that are dominating the system as well. So there is a contradiction in the signals that I've just shown you, but actually what this best illustrates is the contradiction in the way that we do our sampling. We come along and sample a lump of ice. We know nothing about the history of that ice. A whole lot of photosynthesis has gone along, and a whole lot of bacterial dynamics have gone on as well. And we're trying to, out of all of these mixed signals, come up with a coherent story. My guess is it just points to the fact that we really do need the time series by which we're able to kind of unravel, what all of these kind of processes really are. So there is a little bit of a mixed signal. You could read this saying, well, bacteria are the most important things in sea ice, or you could say that the photosynthesizers are as well. Of course, they both completely are. That's tightly coupled. Now, you do get various types of ice habitat, and I'm going to show some pictures in a minute. But what I've been describing up to now is the kind of within this brine channel system. So restricted exchange away from the edges of the ice. And my guess is that where most of the biomasses are formed are actually up at the top here or down at the bottom. Don't worry about that. So, although the most interesting biogeochemical signals that I've been kind of trying to explain just now are going on within the ice, the highest biomasses are actually found at the top or at the bottom. And the highest biomasses are found in the summer in what we call freeboard layers, which are systems that develop just below the surface of the ice or on the underside here. Now, in the Arctic, surface ponds are very much more a feature, but they're being recorded more and more in the Antarctic. So you get communities developing in these ponds, which can have a connection with the water below. So here you have actually a hole through the ice flow. This is meltwater that is overlying the sea. So this was I don't know, it had a salinity of about no more than 10, whereas normal seawater has a salinity of about 30. But what you notice about this, so it's a highly stratified system, it's being held there by purely physical forces, it's a very high light environment, so it's very conducive to a lot of photosynthesis going on. It has a lot of surfaces, and everybody must have put a bottle of water from the tap in a glass bottle and left it on the windowsill, and within days or weeks or maybe months, there's a film of green algae is grown on the outside of the surfaces of that bottle. If you put a diatom from the open water somewhere where there's a surface, it will preferentially grow on that surface rather than growing free in the water. So what you find is that if you've got a lot of surfaces, this promotes a lot of algal growth. Exchange is possible, but grazing is taking place as well. This is rotten ice. So this is where ice flows have been rammed together, jumbled up. It forms this kind of brine, this porridge of mashed up ice. And this mashed up ice is again very buoyant, it's very dynamic, it's held in the surface of the water, so it's held in a high light environment. There's an awful lot of surfaces for the algae to grow on. Exchange of nutrients is possible. There's also grazing going on as well. So this is rotten ice. These freeboard layers are gaps. So you've got a bit of snow, you've got a little bit of ice, and then you've got this watery layer underneath. So this is maybe, I don't know, 5 centimeters. And again, you can see this huge, rich biomass of algal material that's been able to grow. Here you see it again in the profile, some snow, some ice, and then this kind of rotten layer that is very algal rich. Again, it's high light, there's surfaces for things to grow on, exchange of nutrients, so water pumps in and out of here through normal wave action, so it's bringing in resupply of nutrients to the system and also taking waste gases away, so supporting a high biomass. So all of these things, these high biomass regions, provide surfaces, exchange of nutrients, and also flushing through of the system. And the ponds, the gaps, layers, and the surface features are all high habitats. So although the interesting biogeochemistry and the exchange that I kind of was talking about is definitely there and is worthwhile studying, and is what has got a lot of us interested in it, my guess is that biologically these kind of systems are probably very much more important than the ones that are giving the more clear-cut biogeochemical signals. Here you don't measure any of these oxygen and carbon dioxide because the systems are they're basically acting as a filter for the biomass. They're doing no more than kind of filtering the biomass out and holding it stable in a high light environment for it to grow. So we do have a conundrum. This is probably on a global scale very much more important than the more intriguing questions that are raised by the confined environment. And my guess is if I was saying, well, what should we study in the future, as interested as I am about the extreme environment inside the ice flows, my guess is understanding the dynamics at the edges of the ice flows like this is probably where more of the interest should be, or more of the focus should actually be placed. Okay, and I think I would like to finish there actually, and of course I'm able to take the questions, but I think yes. Thank you very much.
Any questions, please? Yes.
So the melted ice had a salinity of 10, and the pores had very high. So this tells you roughly how large part is pore and how large part is.
So if you know the salinity of the bulk ice, and you know the volume of it, you can actually back calculate to know pretty well what the temperature and the salinity was. I mean, those calculations exist.
Is there any life that is connected with ice, but not for photosynthetic, chemosynthetic, for example?
Well, there's bacteria. Well, the bacteria obviously, so they're not photosynthetic.
Right.
Yes.
So they could be at any depth then.
Yes. I mean, the holy grail used to be to look at the succession of algae and bacteria within the ice. But again, because of this problem of the sampling, nobody's really been able to show that to any degree that's worthwhile. Yep.
So how dense is the temporal sampling of the sea ice? I mean, it's obviously much easier to get out in the spring and the fall.
Yeah. So basically, there's a lot of data for spring and fall. Summer ice, there's an increasing amount of data. It's just there's just big black holes in the ether, basically.
And from what you've told us, are there large seasonal cycles in what you see in terms of the biology in the ice, or are you giving us a sort of a snapshot that's typical for spring and fall? Or
So this last set of data was basically very much a summer situation.
Okay.
So it was the cryogenic brines that I showed you with the calcium carbonate, that was late winter, early spring, I suppose. So all of this kind of high nutrient, high biomass, this was very much late spring, early summer kind of when most of the biology is taking place. So that's a warmer period. I mean, you need a certain porosity for things to kind of. I mean, I really do believe in winter. A lot of it just kind of shock. I mean, I think there's just not much going on. There's not enough light to drive very much. You may have the odd bacteria moving around, and the odd nematode. Because some of these nematodes, they're kind of interesting. Some of them can actually just take up dissolved organic matter. They don't have to eat organisms. So you may have them still active a little bit. Yeah.
And I guess my last question is, you said that primarily you get the largest extent of the communities either at the very top of the sea ice or
at the bottom.
On the bottom. Obviously the phase fraction in the ice is greatest at the very bottom, so there's more room to live in
Yes.
the bottom there.
I mean,
But you've got a trade-off between how much light gets into the bottom and it's warm versus lots of light into the top.
Yeah,
it's quite cold.
And for the organisms that are there, I mean, you can see this ice flow. I like this picture because basically the whole of the edge from the snow, but it's not the ice flow itself. It's just the whole of the periphery of that ice flow is covered in biology, where there's a lot of nutrient exchange possible. But actually, probably inside of this ice flow, there's almost nothing going on. So it really is just, this is a higher light environment. We talked about, or I talked about, snow being important for the light environment, of course, but on an ice flow like this, there's a lot of light coming in from the sides as well, which is promoting a lot of that growth as well. So I hate to say it, but I really do believe understanding the processes that are going on at the edges of ice flows are really probably more important than what we've devoted ourselves to for the last 15 years. But maybe not. Oh, sorry.
Yeah, so you say things go down in the winter time. That there's not much happening. Of course, something has to happen.
Yeah. So if we move this ice flow, and we just take this, and this was actually autumn, and say, well, what happens to it in the winter? A lot of I suppose a lot of that biomass will be eroded away and will sink to the seafloor just through normal erosion processes and melting that, just banging into other ice flows is going to knock off big portions of it. Some of that stuff will just go into a dormant state and sit there. But of course some of that stuff will be then finding itself in a layer with a whole load of new ice that is encasing it into making it into an internal community as well.
Right. So I guess my to stretch you a little bit, we were talking about basically these balance of issues, temperature and light.
Yeah.
And in some, when winter begins, the light goes away and it gets cold, and all the open water starts to freeze, and that ice flow, if it doesn't deform, will also get cold and freeze, and so on a much less hospitable place like Enceladus,
Yes.
You have low temperatures. The light doesn't penetrate very deeply, etc. So, is there any information from this system about how long something can be dormant? how, you know, how long can it eke out a living before?
Well, when we're talking about how long things remain dormant, I mean, diatoms, resting stages of diatoms have been taken out of the pyramids, so so basically they can, within Aeolian systems, they can remain viable for eons of times. Bacteria, you know, can remain in dormant phases for very long periods of times indeed. So my guess is these things can all find, I mean, there are measurements that have shown that just to maintain the most basic, just to tick over, they can form these resting stages, what they call physiological resting stages, where they basically go into a, well, I use the term loosely, it's not correctly, strictly speaking correctly, but hibernation, for very long periods of time.
Right. Okay. So it's not inconceivable, for example, that if that things can exist in these environments and or even be transported in ice, for example.
Yeah.
No. Yeah. Okay.
Well, I don't think so, but there's probably people in the audience who are better. That's going to come out.
Yeah. I'm just trying to make you make the terrible decision. Yeah.
That's my interpretation. Well, I only know that because, I mean, a trick question in an interview was that I kind of was talking about this, and some crusty old professor stood up and said, well, yeah, and how long can these diatoms kind of survive? And I said, oh, a couple of years or something. He said, well, what about the pyramids then? So then I went and checked it up, and he's right, you know, we've got viable diatom spores out of urns of who knows what.
Okay, any other questions?
Well,
Yes.
if you talk about things in, let's say, in planets or in other places or in the universe, when it comes out, I mean, you may be able to arrest metabolism and everything, and be able to, well, let it grow again eons later, but you usually have harsh environments and there's damage mechanisms going on, and that would be the limiting rate, I guess.
That has to be the limiting rate, because I mean,
Yeah.
because this isn't particularly harsh. I mean, if it forms a resting spore in the middle of the deep sea, it's hardly harsh. I mean, you know,
Right.
so.
Yeah, extremely low temperature or high osmotic pressure or something. Yeah. Wonderful. Thank
Okay.
you. Yep.
Thank you. Most people have arrived.
Cool.
They told me.
That's why I went and got all these.
Oh, you have it?
Yeah.
Who's arrived? Oh, then you know.
Yeah.